she's going to take us about platinum rubinas.
Thank you. Hello, everybody. I'm going to give you a brief overview on platinum group minerals and some of their synthetic analogs. It's going to be completely different to those who listened until now. There'll be more. I hope it's been not too boring for you, but it's something different. Let's start a little bit of the history of platinum group elements. The first platinum item was found already in Egypt, 700 BC. And La Tolita Tumaco culture in South America that lived in the Esmeralda province and Nariño province, nowadays it's northeast Ecuador and southwest Colombia. They already produced some golden jewelry covered with a thin layer of platinum. And they were, they already made some various objects, platinum coated gold objects, platinum gold sintered alloys, and platinum gold foil plated objects. If you by chance visit Bogota, I strongly recommend to go to Museum of Gold when you can see some of these objects that were excavated there. The first European reference about platinum comes in 1557 when Julius Caesar Scaglier mentioned that in South America or Central America there appears a metal, a mysterious metal that is impossible to melt by fire. However, the main interest for platinum comes in 1748 when Spanish scientist Antonio de Ulloa visited some of the mines in South America because the Spanish miners noted when they were penning gold that because of the similar specific gravity of gold and platinum, they were penning and they were founding platinum that time that they called platina, la plata, coming derived from Spanish. They call it a new silver. And at the beginning, they even threw away the platinum back to the river because they didn't know what to do. And Antonio went to those mines and brought some alloys to Europe, and it attracted interest of many scientists, and they tried to extract platinum. And actually it was extracted or isolated in 1752 only, and it was extracted in England by 3 scientists, and it was, let's say, the first metallurgical attempt how to isolate platinum from iron. Those elements were followed, the platinum was followed by iridium, osmium, palladium, rhodium, and the last discovered and established element was ruthenium in 1807. We all know that the demand for PGE is due to their specific behavior and their characteristics because they're exceptionally resistant to corrosive attack by a wide range of liquids and various gaseous substances. They are stable at very high temperatures, under which other refractory metals are easily oxidized. They have very high melting point. Osmium belongs to the 4 elements with the highest melting points. They are very dense. Therefore, they're all of the significant technological importance because all alloys are exceptionally hard and durable. And as we all know, they are used in catalytic converters because they decrease emissions in automobile exhaust. But even if we move to electric vehicles, we still will need PGE because they are used in fuel cells and also to produce spark plugs. So the demand is still needed. And just for curiosity, 1/4 of the platinum wort production is still used for the jewelry. It's still an investment commodity, but there are plenty of other very important uses of PGE. They are growing recently. In particular, they are used to make nitric acid for fertilizers. Actually, since 2013, it's almost double. They are also widely used in electronics because they increase storage capacities of various batteries. They are also used in glasses to produce fiberglass, LCD monitors, flat panels, and others. And they are nowadays used in a new technology, proton exchange membrane, to produce carbon-free green hydrogen. It is now very popular use of PGE. And of course, they are also used in medicine. They are biocompatible and very well tolerated by body. They are used in numerous treatment, and for instance, even for cancer treatment, and they are used for pacemakers production. The platinum iridium electrodes are used when they're treated with heart diseases. So the more, as you can see, there is a lot of uses of PGE, and the more we know about platinum group minerals, the better we can extract them. So as you all know, the Commission for New Minerals and Mineral Names was established in 1959, and the purpose was to control the introduction of new minerals and mineral names and to make rationalized nomenclature. They were revised by that time, and those that were accepted are termed as grandfathered when you see them in literature, and some dubious were post-discredited. If we look at platinum group minerals up to date, or I can say up to date, I checked just recently the newsletter of IMA, not only up to January, there are 166 known platinum group minerals. However, I have to mention that still there is a number of PGM that require some examination and redefinition, and in particular of its ideal formula and crystal structure. There are still quite unknown phases. And also there is a demand to study in detail the solid solutions, because some of them form, as you all know, solid solution, and we don't know the limits. And nowadays, with the new techniques and development, particularly in new X-ray techniques, there are new minerals described of very small size. We come to 1 or 2 microns, even could be less if it's well described. I just want to give you an example of the redefinition of mineral bragite and wieselskite that was recently redefined. Those minerals were described in, as you can see, 1928 and 1932 and 1962. Louis Cabri and Andy McDonald revised those minerals in detail in terms of crystal structure. And finally, they defined the exact formula from bragite, and they studied the limits of solid solution in the binary system platinum sulfur, palladium sulfur. And we can say that bragite and wieselskite form a complete solid solution, whereas cooperite and bragite has a limited degree. They propose the compositional range where it fits to which parts of this mineral. So it's a very interesting paper. So it's already published in the Canadian Journal of Mineralogy and Petrology. If you look at platinum group minerals, a little bit of statistics, I would say. According to the essential element, the most common group is palladium dominant group, where there are 79 known PGM, followed by platinum minerals, then rhodium, iridium, ruthenium, and there are 4 osmium-rich platinum group minerals. If we look at them in terms of mineral chemistry, the biggest group are sulfides, followed by tellurides, arsenides, intermetallites, selenites, stanites, antimonites, and many others, like you can see. There is even mentioned one oxide, that's a palladinite. However, this mineral is listed, but it's with question mark. It's listed on the IMA list, but I want to mention and point it out that the crystal structure hasn't been proved, and so far none of the platinum group oxide weren't approved by IMA. We know they occur, but they were never properly established with the crystal structure. If we look at platinum group minerals in terms of type localities, the most of them come from Russia, followed by Canada and South Africa, China, USA, and Brazil. And the D deposit is Norilsk Starnak deposits, from where 23 platinum group minerals were described as with the type locality. Since 2002, as you all know, at the time there was a very nice summary by Louis Cabri, who summarized all PGM. And since then, 54 platinum group minerals were discovered. And I just briefly introduce a few of them, not all in detail, of course. There are 3 slides according to chronologically listed those minerals as accepted. I would like to mention that in yellow, actually, I mark those minerals that we try to synthesize in our laboratory. And actually, our aim is to have some kind of database of synthetic platinum group minerals. And we are, of course, very happy to collaborate with some of you if you'd be interested in, because our aim is to have this database and reinvestigate some unclearly known phases. As you can see, there is a white list, a long list of various minerals. I would like to mention some of them of interesting composition, like palladium silicite. There's the first palladium mineral with silicium. There are 2 germanites recently described, and there are many other interesting minerals. What is also interesting, one would think that very simple compositions like platinum, lead, or iron, platinum, they were or must have been already described earlier, but apparently not. There are some very new findings, and there are included the most recent 3 minerals described, let's say, accepted last year, described this year: siderowite, dracopite, and arsenolombardite. Siderowite was found in Kamchatka, and the other 2 minerals in South Africa. Where we still find new platinum group minerals? Actually, the answer is mainly in museums, because most of them were described from the collections that were waiting or were stored somewhere, and people reinvestigate some of the samples. So almost half of them that were observed recently are from old findings. However, there, as you can see, those traditional places for PGM like Russia, Canada, South Africa, Brazil, there are some also less common occurrences where some PGM may be found, like laterites in Dominican Republic or some other interesting places. And I just would like to give you an example that there are really plenty, or there are not plenty, but I'm sure some PGM still in some collections. I would like to give you an example of mineral rotebarite that was collected in 1924 by Professor Hermann Rose in Germany, and it was waiting almost 100 years until it was described and named as a new mineral. That actually happened by chance when Alexandre Cabral started to look at some of the samples looking for plus halide, and actually came across on this new mineral. And very similar happened to koyanenite that was collected by Alan Cradle in Stillwater Complex in 1980, and it was described almost 30 years later. Again, it happens very by chance when I visited Chris Stanley at the National History Museum, and on his desk was the composition of this mineral. He was about to clean the table, and I said, well, look, it might be a new mineral. And actually, we realized that it's exactly a new mineral that we described in about a month later. So I strongly suggest to check your old findings and some of your collections, because there must be some new minerals hidden. Just to briefly introduce them, as you know, some there were named according to the geographical localities. 18 of those 54 were named according to various places worldwide. And some, I would say, really deserve to have a name, like Culverlite, from where many platinum group minerals come from, or Norilskite. And the other group of those minerals were named to honor a mineralogist or geologist in the field of platinum group elements. There are 28 of those minerals named of various people. As you can see, some are our colleagues, some unfortunately aren't with us anymore. And there is the second group of those from who the mineral were names. And there is and the third group, 7 of them were named according to the particular property of mineral, as it's easy to devise from the name, like palladosilicite, palladogermanite, nippolarsite, selenoaurite. And I would like to pay your attention on mineral palladothalite, as is the first PGM containing thallium as a essential element. So those are the PGE that were known from natural. And if we look at the PGM from the synthetic point of view, our aim is to synthesize some of them, because as we all know, very many of them are of very small size. And if we have a synthetic analog, we may study its ideal composition, crystal structure, various physical properties, even thermal stability, and to predict some stable assemblages if we study the phase relations. This is the very, I would say, simple and most common method, silica glass tube method, that is used to produce the synthetic analogs of PGM or other chalcogenides. The principle is quite simple. We use reagents that are placed in silica glass tube. It's sealed under the vacuum, then it's placed into the furnace. It's unleaned or melted, then it's reground under acetone. Again, placed back to the silica glass tube, unleaned and heated for several days, months, weeks, years, depends. Within the platinum group minerals, it requires, I would say, months, not weeks, because of the kinetics. This method has an advantage as we work with a clean, precisely known bulk composition. It permits us visually check anytime the composition and the reaction. Disadvantage is that due to solid state diffusion in some sulfides and some other selenized tellurides, it requires a long time when equilibrium is attained. And excuse me. And another disadvantage is that the product is very fine-grained and it's not always suitable for a single crystal X-ray diffractometry. There are, of course, some other methods that might be used to synthesize PGM, but this is, let's say, the most common and the easiest one to produce synthetic analogs. Just give you an example, when the synthetic analog was used in order to describe a new mineral. It was an example of thalhammerite when we synthesized its synthetic analog, and the crystal structure was solved from synthetic data. And apparently this mineral became quite interesting because it has a unique crystal structure that hasn't been known until now in the mineralogical system. And there are several others, such unique minerals among PGM that have such a structure, like lucularis varite and some other minerals. And in order to prove the identity of the synthetic and natural material, we of course need to have the identical chemical composition, optical, physical properties, crystal structure properties, and in some cases, of course, Raman spectroscopy may help to prove the identity. Not all PGM are really tiny, small, that were described recently. I would like to mention these two minerals in the system, palladium copper and platinum copper, and there is a third one, tomameite. One would think that this system must have been covered already many years ago. Apparently, it has been described quite recently. It's platinum 7 copper, platinum 3 copper, and tomameite, described from Japan, is copper 3 platinum. And those are, in terms of PG, quite big budgets, and the XRD data were collected exactly in situ from the polished grains and compared with synthetic analogs that were already known from literature, and they appear to be identical. So not all of them are so tiny, so sometimes this also can be used in such a way to distinguish them. And if we look at the system, platinum, mercury, selenium, I pick up especially this one because of the mineral jacutingite that I would like to introduce you. It was discovered from Caia iron mine from Itabira district in Brazil in 2011. We studied we studied the phase relations in the system and analyzed the synthetic analogs. We produce synthetic analogs of jacutingite, luberoite, sudovicovite, and timanite. Actually, we prove that there are stable association of those minerals, as you can see. However, I would like to mention this mineral because it has a special properties that have been discovered 10 years later. And actually, jacutingite is a novel quantum spin hole insulator, graphene-like topological insulator. It attracted many scientists from the materials field. And that's what I would like to emphasize, that many of platinum group minerals are not only of interest of mineralogy and geology, but they are also of interest of material sciences. And such phases are used in spintronics. And it became a really big interest for this mineral. There are several papers that have been published using the jacutingite studies because it has a dual topology. It's a very interesting phase, and I would like to mention its palladium analog that we also studied from the synthetic system. We studied palladium, selenium, mercury experimentally, and that time when we studied, we came across of a, I would say, new phase that were also observed in Hope Snows, Devon in England. Actually, at the time we even had a working name for this mineral, Hope Snowside. But the group of Ma, they discovered this phase also from Tilkerode in Harz Mountains in Germany, and they're a little bit faster, and they name it Tilkerodeite, but never mind. The most important thing, that mineral is out. And it's a palladium analog of jacutingite. This is isostructural with its platinum analog, and it's also of interest of material sciences because of its special properties. It's also dual topology, but it's not new one because jacutingite was the first one. But I want to mention that those phases are also very often of interest of material sciences. If we look at the experimental data for a ternary system that haven't been studied yet, there are quite a few systems containing iridium that haven't been covered at all experimentally, that however they'll be needed, and it's important to know them in detail because all of them contain a ternary mineral. There are also several with palladium in the system that are of interest. Particularly, there are still unknown the stoichiometry and ideal formula of stanopalladinite or timerite. And apparently it looks like the chemical composition is the same, just the difference of the structure. And there are plenty of other ternary systems that needs to be experimentally covered. We are now working on palladium antimony selenium system, palladium tellurium and selenium system, and jointly with our group from Chernogolovka, we work on platinum bismuth tellurium system. This is just a very quick overview what the experimental study can tell us. As I already mentioned, we can study various structural processes in details, and we may apply it also the limits of solid solution that we can define experimentally is much better and explain how it's formed at natural conditions. But I would like again to emphasize that many of platinum group minerals are of interest of material science because they are semiconductor and also two-dimensional materials. Just briefly sum up, as I mentioned, there are 166 platinum group minerals approved by IMA up to date. Still, there are some minerals that need to be re-examined in detail in terms of ideal formula, and there are still some additional system that needs to be covered. Thank you very much for your attention.
We have time for the questions. Any question?
Yeah, thank you, Anna, for this talk. And I have a question regarding the experimental work and the more stranger composition with PG oxides and silicates. Is this also possible to synthesize, or would we need a different approach for these?
It's quite difficult to synthesize, exceptionally the methods that we use. Yeah, we tried to synthesize some oxide, but we weren't really successful because it's difficult to make real oxide because sometimes you have a hydrogen there. So then you don't know whether it's a hydroxide or just oxide. Yeah.
Any other question?
Just a very small question. Just a very small question about silicite. Where was it found, in which conditions? Because it sounds so strange.
Yeah.
The palladium to
It was,
silicates?
yes, it was found, there was two places, South Africa and Tanzania. I suggest to have a look at the paper of Louis Cabri. Actually, he described it. You will see all the details there.
Thank you.
Okay, we move to the next one. Thank you.
Right, I set myself up.
Okay. Next one is by Butcher. 25 years on discovery of PE from